Have you ever wondered how the structure of an atom came about? How did we decide that, okay, this is how we will represent um, an atom? So here's an example of the Bohr-Rutherford atomic model. Let's see how nowadays in the school, in my class, I show my students how to do this. But how come we ended up saying, okay, this is the way to go? So let's see what we can do about this topic. When we think of matter, we can think of particles. Now, particles can be of all kinds of size, but even though they are very tiny. When you think of a particle, you can think, for example, of this copper wire. If I take this copper wire and I cut it in half, and I cut it in half, and I cut it in half, eventually I'm going to ended up with a tiny little piece of copper. That tiny little piece of copper cannot be divided anymore. It is what is matter. And that matter, we call it an atom of copper. But the whole idea here is how we can better understand the evolution of that idea. So first of all, an atom is a basic unit of a chemical element. So I'm going to put here a link to a video I just did on the periodic table on how we organize the chemical elements. But first, let's see how this idea of atoms, this atomic model came about. So here I'm going back in the past. We have Asherian Canada in about, let's say, 2,500 years ago, even more. He was an Indian philosopher. So here we're not quite sure on the date. And he was thinking as a philosopher about matter, what was. And here he defined matter as being four things from what he could see. There's air, water, earth, and fire. Now, over the years, what happened is that we have, so this was in India. We also have so here we end up in Europe, we have Democritus about 2,500 years ago. And here his idea was that the substance are made of eternally unchanging, indivisible particles. So that means that if you have different matter, you have different substances. So here we have a variety of little shapes. That means that different metals have a different shape of particles. For example, we knew about gold, we knew about silver, copper, because for the last couple tens of thousands of years, we had the evolution of our modern society. So that was Democritus. But a few years after, we also have Socrates. No, it was Aristotle. And Aristotle says, no, that quite doesn't work. So here I was looking at my research, and about 2,300 years ago, he mentioned that empty space cannot exist. So that was one thing. And that matter is made of earth, fire, and water. So you could see here that at this time, if this idea of oxygen or this idea of gas was not quite understood. So let's see if we can go a bit beyond. We also have here about 2,100, 2,200 years, we have this evolution of ancient China. Some of you may recognize some of these symbols from different cultures and maybe some media you've seen. So here we have water, wood, fire, earth, and metals. For the same way we have in several hundred years, we had the indigenous medicine wheel. And here we have, for example, air, we had fire, we had water, and we had earth. So if you see around the world, we had similar ideas, philosophically speaking, on what matter was. And that brings us to what I talked about in my classroom. The theory is Eurocentric, I do understand, but at the time I knew that there were scientists that were developing this idea of atoms in Europe, in Asia, in Russia. And these individuals were often getting together to chat about their discoveries so that they can learn from each other to advance science. So the first person we're going to talk about is called Dalton. Dalton here came up with the four basic principles of what an atom is based on what society knew at the time. So the first of all is that all matter is made of small indivisible particles called atom. And even though the word atom existed from before, so here he used what people knew. All the atoms of an element are identical in properties such as size and mass. A little bit in line with what Democritus had discuss. Atoms of different elements have different properties. So here his idea was that if you have a gas or a solid, a metal or otherwise, they have different mass and density. And we also have atoms of different element can combine with other elements to create new substances. So that's something we knew. And that was based, for example, in the evolution of metals and alloys that people use to create bronze, for example, or other alloys that are metals. So here are some of the elements that Dalton had categorized at some point, keeping in mind that each of these elements had their own specific particles. So here we can recognize iron and copper, lead, indeed, silver and gold. But they also knew about mercury, which was a liquid metal. They knew about carbon. So when you have a campfire, you have black soot. They knew about this and a few other elements. Keeping in mind here that lime and soda and potash, some of these were used in as part of creating soap, for example, and other substances. Even though these are not in 2024 elements, they are not considered molecules, but at the time we did not know, and that's kind of fun. Let's go to the next bit. So here we are at 1808. Now we're going 100 years in the future. Now at that time, scientists were playing with electricity. They were already putting together batteries. So some in the early 1900s, we had the electric cars already, and Edison was trying to see if he could create that bulb of his and making sure that he could make it better. So here we have Thomson playing with electricity, and he realized that when we have particles and we get particles through magnets or a coil having electricity, particles were actually changing direction. So that means that the observation he had was the fact that these particles were no longer going into a straight line, they were being bent. And here you had the screen, and he noticed that. Okay, so if that's the case, that means that we have particles, like Dalton said, but within those particles, we had to have what he called a particle that was neutral. And we knew that. Let's see if I can make it smaller. There we go. Can we make it this way? That's even better. So we had particles that were neutrals, but we had charges in them. We already knew about electricity, and for them we had, like, for example, a copper wire, and particles flowed through them. So we had the idea of electrons. So what he did is we had particles that are positive, and we have little electrons that are here and there all over the place. And the idea here was we have like a raisin bread here. It could be a chocolate chip cookie. So we have an overall matter with little specks and bits in between. And he knew that because it reacted with the electrons of the electricity of experiment. So this was a new model that he had, keeping in mind that Dalton was also someone who created this idea of particle based on previous philosophies. So here we have a couple of years later, Rutherford. So Rutherford was a scientist in Europe, came to Canada for a couple of years and went back to England after a while. So here he had a particle beam that was going through here, a piece of gold. So his idea was at first that if we have a beam of particle going through matter, then what will happen is those particles will be bounced back. That was his idea, because a matter hitting a matter will be pushed back, knowing that Aristotle said that there's no empty space. But what he realized is that as the particles were going through the piece of gold, many were going through. So that was interesting. But he also noticed that on either side, you had little somehow particles that were not following the main beam and were going on either side. So what he did is at some point he just kept putting his sensors all around to try to cover as much as a 360 degrees. And then he realized that even though most of the particles went through, some of them were deflected by something. So his new theory here came about. So in the Thomson model, things would not have gone through, But here he knew that most went through, but some change direction. Same thing if you're playing pool or you're playing bowling. Sometimes you're sending a ball hitting something else, and it would change some of its direction. Perfect. So here he figured that in the middle of a particle of matter, you had to have a very dense center. The dense center was what was creating these deflection of his particles. But he also know that within the particles within the atom, there was a lot of empty space because a lot of these particles were going through. So that's his idea that the new particle that was put together with Dalton with a spherical idea. And here that we had negative parts within a neutral particle. Here Rutherford says, okay, we have a particle following Dalton and Thomson's idea. We also have most of the density inside in the middle. That's why we have deflecting particles. But there's a lot of empty space which allows his particles to go through. And that's why he put in the middle most of his dense part, and he called it the positive part of the atom, and he put all the electrons around. So all the electrons around with the positive in the center made this particle neutral. And that's how we get this idea of an image of here an atom. So that was Rutherford's contribution. Now, Rutherford had a student, and his name was Bohr. So here Bohr figured, okay, Rutherford is my teacher, he's smart, he knows stuff. But here, let's see if I can show you something interesting. You've seen this example where we have phosphorescence. So his idea here, he did all kind of experiments, but this one shows nicely what it is. You end up with an object that absorbs light, and when you turn off the light, then you have an object that glows in the night. So his idea is, okay, somehow we have matter when the light is touching them. This matter is attracting energy, but after a while, if you turn off the light, that means that this energy is released, but with delay. And that was the basis of his new discovery of the model of the atom. So here he says, it's coming. So if we have an atom and we have in the middle my positive nucleus, you have energy coming in. So an electron that is on this layer here will absorb energy, and the electrons will change level of energy. So you think, for example, of you've got little kids, they're gathering around a game, someone wins, gets energy, starts running around the group, and after it runs around a little bit, then it calms down and goes back to play the game again. So that was his idea. So we have electrons that were gathering energy. The electrons will be going at a level a bit further from the nucleus, and still attracted because electrons are negative and protons are positive. And eventually this electron will go back to its original energy level, and then some energy will be released with a delay. And that explains, for example, phosphorescence. So in order to be able to do this, Bohr says these electrons that are around the nucleus, like Rutherford had mentioned, they ought to have a place where they are located. So his model is that on the first level, there'll be 2 electrons. On the second level, there'll be up to 8 electrons, and then afterwards. And this is what we call the Bohr-Rutherford diagram. Now, I'm going to add something. I don't know, the time is moving on. I know it's a longer video, but that explains the whole history here on how it goes. Now, in the meantime, so just before we had here Thomson, so between Thomson and Dalton, elements were being discovered. And here, let's see if I can. So here we had a scientist. I know it's in French, but he's Russian in 1869. His name was Mendeleev. So here we had more element than Dalton had. And then he started to organize them so that he could put together elements with similar properties. So he realized, for example, that many of these, so beryllium, boron, carbon, nitrogen, oxygen, fluorine here, they have similar, you could put them in a trend, but somehow that this bunch here was not the same as this group here. So he was organizing some of his elements that were known at the time. And the beauty of Mendeleev is that he even had places where he had empty spots here with interrogation point, and here as well, where there was unknown elements, but he was able to predict that some elements were not discovered yet, and they would take those spots. So Mendeleev did an amazing job there. So here you could see it's organized with 2 here. We have 7 or 8 elements on this side, and we have some on this one right here. And if you look at the periodic table, what do you see? It is organized in a way that is helping us understand how the elements are working together with similar trends. So it's quite nice on his part. So that is this one here with Bohr Rutherford. So here I'm going to see if I can do a video with examples on how to trace the Bohr Rutherford diagram, but let's continue with the continuation of the atomic let's say model and its evolution. The next bit I want to talk about, and we're coming to the current known structure of the atom, we have what we called Chadwick. Chadwick here realized that we have atoms that are similar, that means with a similar atomic number. And the reason why they are similar is that the atomic number 8 is the identity of an element. So if I show, so here we have an atomic number of 8 with O as its symbol. Let's look at the periodic table. Oxygen is right here with an atomic number 8. It has its spot on the periodic table, and there's an atomic mass as well. So let's continue. So Chadwick said, okay, we have atoms that are the same, but somehow their mass is different. So here what is interesting is that Chadwick had to figure out how can we have similar elements, similar atoms, not similar elements, similar atoms because they have the same identity, but their mass is different. So you could you could think of, if you think of a kid who's 5 years old, and his name is Arthur. Arthur, as he grows up and he becomes a teenager, is the same Arthur, but he's much heavier. So let's see. You have to figure out how can we account for atoms that have the same identity but different mass. So that he put together this idea of neutrons that must exist. And this is the last particles that came into the atomic model. So let's see. So this is the current idea of an atomic, a Bohr diagram with the current atomic model. So we have in the center the nucleus here where most of the mass is for an atom, and it has a positive charge here, and we have within the nucleus also neutrons. They have no charge, but they act a bit like a glue. They're keeping the positive protons together. Otherwise, they will just want to fly apart because they're all positive and the same charge. So we have the nucleus here with almost all of the mass, and surrounding this nucleus, we have electrons, and they are going at specific levels around that nucleus, which includes this idea that Dalton came up at some point, all previous philosophers, with Thomson and Bohr and Rutherford and Chadwick. So you could see how the theory of the atom, the atomic model, has evolved over the centuries. And this is my story of the evolution of the atomic model. If you have any clarification with respect to this theory, put them in the comments below. I'm here to answer your question, and I use your questions to bring new ideas to this channel. If you've enjoyed this video so far, don't hesitate to subscribe to our channel. Do a thumbs up. We're doing a live show every Saturday at noon, Toronto time in Canada. You're always welcome. And otherwise, I'm going to put on the side another video for you. So I'm going to put a link to another science video. You'll see you're going to learn something more. And I'm going to put a video here on the periodic table. I think you'll enjoy that. I'll see you there.